On September 21, 2003, a woman named Claudia Alexander gave the order to destroy one of the most successful spacecraft in the history of space exploration, and to destroy it at a time when it was still fully operational. By that morning, she had been leading the grand Galileo project for 3 years. The machine itself had been in the freezing depths of space for 14 years. Its scientific instruments were sending priceless data back to Earth every single week, and absolutely nothing had broken on board that the brilliant team of engineers hadn't already learned to bypass a dozen times over. And yet, on that September morning, with cold calculation, Alexander approved a trajectory that steered the spacecraft into the dense layers of Jupiter. At a speed of about 48 kilometers per second, it slammed into the gas giant. The dense atmosphere tore apart, melted, and vaporized the spacecraft in less than a minute. It wasn't about the budget, and it wasn't a hardware failure. The great Galileo was sentenced to death because of a single measurement. A measurement taken 4 years earlier near a tiny, icy moon. A moon that Earth's technology is strictly forbidden to land on to this day. There is a place in our solar system that NASA has consciously decided not to touch, and the threat there comes from a completely different direction than we are used to expecting. Everything we know about this world was gathered on the fly by a single instrument, hurtling over its icy crust at a speed of 15,000 kilometers per hour. But as soon as this instrument did its job, the mission it belonged to became a planetary scale threat. Continuing the flight was no longer an option. Let's plunge into the darkness and figure out exactly what they found out there. Galileo's long journey began on October 18, 1989. The spacecraft left Earth in the dark cargo bay of the Space Shuttle Atlantis. 2.5 tons of highly complex hardware, electronics, and hope set a course for Jupiter. Except the route, if you look at the diagram, looked absolutely absurd. At the time, NASA didn't have a rocket capable of throwing that much mass directly to the gas giant, so first, the spacecraft dove toward a scorching hot Venus, then returned back, flying past Earth twice, stealing kinetic energy bit by bit from each planet. Only after 6 years of this gravitational roller coaster did Galileo build up enough speed to finally break out into the outer darkness of the solar system. But a terrible price had to be paid for this long run-up. A year and a half after launch in April '91, engineers sent a routine command: deploy the main high-gain antenna. It was a colossal mesh dish, 5 meters across, folded up before launch like an umbrella. It was through this antenna, like a wide highway, that the entire stream of scientific data was supposed to flow. The signal went out. The mechanisms fired. But 3 ribs out of 18 were hopelessly stuck. It took 3 agonizing years of desperate attempts to free it. Engineers turned the half-open antenna directly toward the scorching sun so the metal would heat up and expand, and then abruptly swung it into the freezing shade, hoping the thermal shock would snap the jammed mechanism loose. The tiny deployment motor was turned on and off more than 13,000 times. They literally shook the spacecraft in the vacuum of space. Nothing worked. The bitterest explanation the team eventually arrived at went like this. During the long years of storage in warehouses and the endless truck rides across the states before launch, the factory lubrication on the alignment pins had simply worn off. Bare titanium met bare metal, and in the vacuum of space, they welded themselves permanently together in a process physicists call cold welding. The only thing the mission had left at its disposal was the backup low-gain antenna, a tiny metal horn designed exclusively for emergency engineering signals. Just think about these numbers. Instead of the planned 134,000 bits per second, this little thing could output a pathetic 10. Hold on to that thought for a second. Almost the entire bandwidth capacity of the spacecraft had vanished without a trace in the vacuum. And Jupiter was still 5 whole years away. Any other space agency would have declared the mission dead. But what the JPL team did next, engineers still remember with awe. Instead of accepting a crippled mission, they sat down and wrote entirely new onboard software. And then, packet by packet, they uploaded this code across hundreds of millions of kilometers of void into the spacecraft's flight computer. A computer whose active memory was smaller than a modern pocket calculator's. The new code worked miracles. It compressed images right on board before sending them, ruthlessly threw out redundant data, and squeezed the volume of every measurement using incredibly complex statistical tricks. At the same time, on Earth, they urgently upgraded the giant dishes of the Deep Space Network, combining them into a single system to catch even the faintest whisper from the dying spacecraft. As a result, the rebuilt system was able to reach about 1,000 bits per second. By the standards of the original design, this still seemed like a disaster, but by the standards of certain death, it was salvation. Engineering genius returned to humanity about 70% of the promised science. On December 7th, 1995, the heroic Galileo finally reached Jupiter, becoming the first artificial satellite of a planet in the outer solar system in history. Orbiting Jupiter in an eternal dance are 4 colossal moons, discovered long ago by Galileo Galilei. And the new iron Galileo was supposed to study them all. Io turned out to be the most volcanically active body known to science, violently erupting fountains of sulfur 300 kilometers above its own surface. Ganymede, to the total shock of astrophysicists, was found to have a powerful magnetic field of its own, unheard of for a moon. Callisto appeared before the cameras as an ancient, heavily scarred, absolutely dead world whose geological history had long since ended. And then, the cameras turned to Europa, and it didn't fit into any existing theory. The first thing that struck planetary scientists was the eerie absence of craters. In space, any solid body acts as a target for asteroids. Crater counting is the gold standard of dating. The longer a surface is exposed to space, the more impact scars it accumulates. Our moon, or Callisto, is pockmarked with craters, preserving the memory of 4 billion years of cosmic bombardment. Callisto is in the exact same system, catching the exact same cosmic debris as Europa. But across the entire surface of Europa, researchers found fewer than 30 craters larger than 20 kilometers. It was as smooth as a cracked billiard ball. If you run this data through mathematical models, the answer comes out incredible. The surface of Europa simply cannot be physically older than 40 to 90 million years. And this is despite the fact that the moon itself formed alongside Jupiter 4.5 billion years ago. This meant only one thing: something was wiping the moon's geological record completely clean. over and over again. In the geologically recent past, the surface was renewing itself, and science had no reason to believe that this process had stopped. Then, scientists started studying the strange markings. Dark, rusty brown streaks stretched across the ice for thousands of kilometers. Some were nearly 100 kilometers wide. They crossed and overlapped each other in complex layers that geologists could literally arrange in chronological order. They called them lineae. In places, the ice shell looked monstrously stretched, as if something warm had risen from below right into a gaping tear and frozen into a fresh crust. In other regions, which researchers aptly dubbed chaos terrain, the icy crust looked shattered into giant rafts. These rafts had clearly shifted, rotated on their axes, and frozen back in at an angle, exactly like the jagged blocks of river ice during a spring thaw on Earth. A dead ice ball just sitting on a rocky core does not behave like this. The answer, it seemed, was lying on the surface: tidal heating. Europa's orbit is constantly distorted by its gravitational neighbors, Io and Ganymede. Because of this, its orbit isn't perfectly circular, but slightly elongated. Its distance to the giant Jupiter is constantly changing, and along with it, the tidal force changes monstrously. Jupiter is literally stretching and squeezing Europa. The entire body of this moon is physically kneaded every 3.5 days, and this process has been going on non-stop for 4 billion years. The constant flexing of solid rock generates a massive amount of internal heat. And at that depth, this heat is more than enough to melt water ice. But despite the logical strength of this argument, it remained just a hypothesis on paper. Debates about the interiors of worlds that are hundreds of millions of kilometers further from the sun than Earth are not resolved by beautiful theories alone. Ironclad proof was needed. The instrument that forever settled this question and changed our understanding of the universe belonged to Margaret Kivelson, an outstanding physicist from the University of California who headed the mission's Magnetometer team. While everyone was waiting for pretty pictures, her device did just one thing, quite boring to a layman. It measured the magnetic field. The magnetometer hung on a long boom, extending 11 meters from the main body of Galileo so that the noisy onboard electronics of the spacecraft wouldn't drown out the delicate cosmic signals. Jupiter has the most colossal and deadly planetary magnetic field in the solar system. It is offset and tilted by about 10 degrees relative to the giant's axis of rotation. Because of this tilt, and because Jupiter makes a full rotation on its axis in just 10 hours, any moon inside this field gets thrown into a magnetic meat grinder. The external field rocks back and forth, crashing over Europa on a strict, relentless schedule. Basic physics taught in high school dictates, if a changing magnetic field passes through a good conductor, it induces electrical currents within it. And these currents, in turn, generate their own magnetic field, directed exactly opposite to the one that created them. Absolutely every electrical transformer on planet Earth works on this simple principle. From 1996 to the year 2000, the crippled Galileo made many close flybys past Europa, and Margaret Kivelson's magnetometer repeatedly picked up exactly this signature. Europa was generating its own magnetic field, and it flipped in precise rhythm with Jupiter's rotation. The strength and orientation of this response were exactly what you would get from a giant, electrically conductive shell hidden very close to the moon's surface. In the summer of the year 2000, Kivelson's team published a historic paper in the journal Science. It was a triumph. There was just one catch. Solid water ice does not conduct electricity. Cold rock does not conduct electricity at a level that could create such a powerful signal. Given the moon's known density, at that depth and in such a cyclopean volume, this magnetic signal could correspond to only one substance: liquid, concentrated, salty water. The numbers that came out of the rigorous mathematical fitting of the data became the reason for everything that happened to the spacecraft next. This conductive layer had to lie frighteningly close to the surface, within a couple of tens of kilometers, and it had to be unimaginably thick. Current geophysical estimates put the thickness of the ice shell at 15 to 25 kilometers, and beneath it sloshes a global dark ocean, 60 to 150 kilometers deep. Europa is actually slightly smaller than our moon, but the liquid water hidden beneath its ice shield is roughly 2 or even 3 times the volume of all the oceans on our Earth combined. And what is most astounding, the floor of this extraterrestrial ocean is rocky. This means that liquid water and mineral-rich rocks are in constant direct contact. Gravitational tidal flexing continuously pumps giant volumes of thermal energy into this system. On top of that, chemical compounds from the radiation-oxidized icy surface of the moon appear to slowly seep down through deep cracks. This cycle is capable of delivering chemical energy into the dark depths as well. Biologists searching for extraterrestrial life always list 4 fundamental conditions for its emergence: liquid water, chemical elements, an energy source, and a sufficient amount of time. Europa meets absolutely all 4 conditions, and this giant chemical laboratory has been running without a single break for about 4 billion years. No one on the Galileo team dared to state publicly that there was definitely life down there, but ruling out its presence was now absolutely impossible. And the fate of the entire mission hung on this tiny probability. The legal framework that ultimately killed Galileo was written long before the first human set foot on lunar dust. The fundamental Outer Space Treaty entered into force in October 1967 at the height of the Cold War. Most people know this document for its loud clauses banning the placement of nuclear weapons in orbit and the rule that celestial bodies cannot belong to any sovereign nation. But hiding in Article 9 is a modest phrase that has since served as the invisible hand guiding the design of absolutely all interplanetary missions. States shall pursue studies of outer space, including the moon and other celestial bodies, and conduct exploration of them so as to avoid their harmful contamination. With this single line, protecting other worlds from so-called forward contamination turned into the strictest international obligation. The only problem was the treaty didn't have a single word about exactly how clean a launched spacecraft had to be. Filling this technical gap fell to the International Committee on Space Research, known as COSPAR. It was they who developed the planetary protection policy that all space agencies around the world still live and work by today. COSPAR sorts all missions based on 2 criteria: the type of target body and what exactly the spacecraft will do upon arrival. A simple flyby of a dead asteroid, where even pre-biological chemistry is impossible, sits at the very bottom of the strictness scale and requires almost nothing from engineers. But if you are building a lander for a place where Earth organisms could theoretically survive, reproduce, and spread, you find yourself at the very top of this scale. Every part of the spacecraft is ruthlessly baked in ovens, wiped down with toxic solvents, and assembled in chambers under constantly filtered air. And then microbiologists walk around and literally count the surviving bacterial spores per square meter of metal. They count them one by one, with every microbe meticulously recorded in an official document. COSPAR treats Europa with special attention, and the requirement for it isn't defined by a strict cleaning procedure. It is defined by a harsh probability. The number that forms the basis of this policy sounds like an absolute verdict. The chance of contaminating Europa's subglacial ocean with Earth life must not exceed 1 in 10,000 for an agreed-upon window of several decades. Anything that goes beyond this microscopic chance is considered an international failure. Any mission whose route passes anywhere near Jupiter is required to prove mathematically that it will not introduce a viable Earth organism into this alien water, even under the worst-case scenario. But that can only be proven by someone who has complete control over their spacecraft, and a dead spacecraft with empty fuel tanks answers to no one. You can argue all day about whether this planetary protection rule is a form of paranoia, but the truth isn't born in offices. It's born in real-world testing. What is actually capable of surviving on the hull of a spacecraft in open space. Satellite assembly takes place under brutal control. The air is filtered, the humidity is regulated. Technicians are sealed in white suits from head to toe, leaving only their eyes exposed. The metal is wiped with the purest alcohol. Some components are sterilized for days with extreme heat, but the resultant object is still not absolutely sterile. And no one in the space industry even pretends that it is. That is exactly why the COSPAR requirement is written not as a 0, but as an allowable number of surviving spores. 0 is simply unattainable. What survives are mostly bacterial endospores. And microbiological surveys of NASA's sterile clean rooms yield a frightening result time and time again. The genus Bacillus reigns supreme there. This bacterium possesses an incredible survival mechanism. A spore tightly packs its DNA beneath impenetrable layers of a protein coat, hiding it in a dehydrated core. In this state, it doesn't eat, it doesn't divide, it doesn't breathe, and it practically doesn't age. And it can hold this deep hibernation mode for many decades. Spores that scientists intentionally attached to the outside of the International Space Station and left in a harsh vacuum for 18 months, battered by temperature swings and scorching unfiltered solar ultraviolet radiation, return to Earth with living colonies. And there are cases that are even worse. The bacterium Deinococcus radiodurans, jokingly nicknamed Conan the bacterium by biologists, easily withstands radiation doses thousands of times higher than what is lethal to a human. In real time, over a matter of hours, it simply reassembles its radiation-shattered genome from the fragments. This microorganism was first isolated not just anywhere, but from canned meat that had been intentionally irradiated with gamma rays specifically to sterilize it. For decades in the corridors of NASA, a famous story from the Apollo 12 mission was passed from mouth to mouth. In November '69, the crew made a pinpoint landing close enough to the old robotic Surveyor 3, which had stood silently on the moon since April '67. The astronauts walked up to it and literally snipped off pieces of hardware with tools. A camera part was brought home in a sealed container, and soon after, the lunar receiving laboratory stunned the world. Right from inside the camera's foam insulation, they extracted a living microorganism, Streptococcus mitis, an ordinary, mundane bacterium from the human mouth. And it had apparently remained alive after 2.5 years in an absolute vacuum, under harsh cosmic radiation and wild swings in lunar temperature. In fairness, this legendary result was later seriously re-examined. A meticulous analysis in the year 2011 brought up the original archival film of that very camera being opened and found a critical vulnerability. The analysis was conducted without complete biological contamination control, and technicians were working near the alien hardware with their sleeves rolled up. It is equally likely that the organism got onto the part while already on Earth, inside the laboratory itself, after its return. Who sneezed on the camera? An astronaut before launch, or a lab technician after landing? No one knows for sure, and honest scientific reports say exactly that today. But regardless of who is right in this historical debate, the big picture hardly changes. The entire philosophy of planetary protection is built on the fact that the risk of contamination cannot be completely eliminated. And no biologist in their right mind would risk ruling out the possibility that a living, aggressive Earth extremophile, having made its way into a warm, dark, nutrient-rich, salty ocean with a rocky bottom and a 4 billion year evolutionary head start, would begin to multiply there. By the year 2002, Galileo had spent 7 years in Jupiter's brutal system. During that time, it took a radiation beating that no designer had ever prepared it for. Jupiter's radiation belts are the harshest, most electronic scorching environment any man-made spacecraft has ever operated in. And because the volcanic moon Io orbits right inside these deadly belts, studying the inner moons required Galileo to cross this region over and over again, taking hit after hit. Over the course of the mission, the electronics absorbed a staggering dose, more than 600,000 rads, which was 4 times the spacecraft's original design tolerance. The consequences were dire. Radiation-induced memory errors piled up constantly. The magnetic tape recorder, which was vital for saving data, once jammed solid from wear and tear, and engineers literally had to coax it back to life with clever commands. Priceless scientific instruments began to fail one by one, and mission commanders nursed them back to health individually, like doctors in an intensive care unit. But what signed the mission's final death warrant was something far simpler and more primitive than radiation. On board, the fuel was irretrievably running out. Absolutely all control of a spacecraft relies on its reserves of hydrazine. It is with tiny bursts of the maneuvering thrusters that engineers point the antenna at Earth, correct the orbit, and decide where the machine will fly next. As soon as those tanks run dry, the spacecraft turns into a piece of dead rock. And then, any random trajectory becomes a one-way ticket. The Jupiter system is the absolute worst place in the universe for a random trajectory. The 4 giant moons constantly perturb the orbit of any object passing by. The slightest gravitational nudges accumulate and over decades lead to chaos. Claudia Alexander took the helm of the massive project in the year 2000. She was only 40 years old, and soon, a ruthless long-term calculation landed on her desk. The navigation team took the likely final orbits of the weakening Galileo and ran a supercomputer model decades into the future, meticulously tracking exactly where the gravitational currents would carry the dead, uncontrollable spacecraft. The model didn't give a 100% guarantee of a collision with Europa, but it showed an absolutely real mathematical probability of such an outcome, smeared across a multitude of possible future scenarios. And given Kaspar's strict threshold of 1 in 10,000, this meant failure. Engineers laid saving options on the table, only to sigh and take them right back. Parking Galileo in a wide, safe orbit far beyond the orbits of the moons required much more fuel than was left in the half-empty tanks. Attempting to permanently eject the spacecraft from the Jupiter system via a gravity assist required even more energy. The remnants of the precious hydrazine were enough for only one final act, a guaranteed, controlled entry into the atmosphere of Jupiter itself. Jupiter, as a gas giant, has no solid surface to crash into. Any spacecraft in this raging atmosphere heats up to thousands of degrees in a matter of minutes, is crushed by monstrous pressure, and literally vaporizes into plasma. And any microscopic speck of dust sinks forever into depths and pressures where no complex organic molecule could ever survive. Out of all the disposal methods available in that system, this one carried absolutely zero risk of contaminating Europa. The decision was formally made in the year 2000, 3 long years before its inevitable execution. The final, fatal trajectory was set during a gravity assist flyby of Amalthea, a small inner moon of Jupiter, in November 2002. That brief encounter delicately bent Galileo's path so that, exactly 10 months later, it would return to the gas giant, straight into its clouds. On September 21st, 2003, the main control room at JPL was filled with people. Many of them had given the best years of their lives to this mission. Some had been working on the spacecraft for 20 years, if you included the early development stages. Some of the esteemed scientists in the room were nothing but green grad students when the space shuttle launched. Claudia Alexander was in the room. She stood at the helm and with a heavy heart guided this final process. Galileo plunged in over the dark night side right at Jupiter's equator at an inconceivable speed of about 48 kilometers per second. And, like a true explorer, it desperately transmitted scientific data all the way down. Its last fade-in signal went out into open space at 11:57 a.m. Pacific time. Due to the colossal distance to Earth, this signal traveled through the void for another 46 minutes. So by the time the technicians in the room finally locked onto the flat noise of the void and silence fell over the room, the machine itself hadn't existed for 3/4 of an hour. It had long since become a part of Jupiter. But even as it died, the spacecraft fought. The scientific instruments returned unique data right up to the very end, measuring the dense, scorching environment through which the craft was falling into oblivion. To this day, It remains the only direct sampling of Jupiter's upper equatorial atmosphere in history by anything other than the small probe that Galileo itself dropped into the planet's atmosphere back in 1995. Yes, those last 20 seconds of the spacecraft's agony didn't yield any clear scientific result worth a separate publication, but getting one was never the main goal. The numbers that historians proudly repeat today go like this: 14 incredible years of work in space, 35 successful orbits around Jupiter, the transmission of about 30 gigabits of priceless scientific data, and all of this through a tiny antenna while the main one never once opened. But the number that decided everything on that September morning was a dry standard from the planetary protection rules. And to comply with that standard, they had to cold-bloodedly destroy the great machine whose discoveries had made the rule necessary in the first place. After the death of Galileo, the brilliant Claudia Alexander managed the American portion of another landmark mission, the comet probe Rosetta. To the immense sorrow of the scientific world, she passed away from cancer in July 2015. She was only 56, and Margaret Kivelson, the very physicist with the Magnetometer whose instrument found the subglacial ocean that condemned the spacecraft, continued publishing scientific papers on Europa for another 2 long decades. And she lived to see the day when a brand new mission launched from Earth, built specifically to return to her discovery. The Europa Clipper spacecraft roared off the launch pad on October 14, 2024. To this day, it is the largest and most expensive spacecraft NASA has ever built for a planetary mission. Its colossal size is primarily due to its gigantic solar panels, which are critically necessary to collect dim light at such an incredible distance from the sun. Clipper carries 9 of the most advanced scientific instruments aimed at answering one fundamental question that has tortured us since Galileo. Exactly how thick is this ice shield? How deep is the ocean hidden beneath it? And is there anything at all in this alien chemistry worth sending a lander for? But Clipper will not orbit Europa itself. Part of the reason is the deadly radiation. An orbit around Europa means continuous round-the-clock exposure to the worst, densest part of Jupiter's radiation belts. No electronics will last long there. And the rest of the reason is the main theme of our story. Engineers found an elegant solution. Clipper will fly in a highly elongated, elliptical loop around Jupiter itself. It will make rapid, close flybys past Europa about 50 times, greedily collecting massive amounts of data in short sprints. And it will spend the remainder of each long orbit in much quieter places, far from the radiation. This complex orbital dance guarantees that the massive spacecraft stays out of any random trajectories that could end in an uncontrolled crash onto the icy moon. Of course, the harshest planetary protection procedures were applied anyway. The biological payload was controlled, and spores were meticulously counted at every stage of the long assembly. A plan for safe disposal at the end of its long life is already baked into the project. The current baseline scenario is to steer the decommissioned spacecraft into Ganymede. Ganymede's ice is much thicker. The presence of a similarly shallow ocean in contact with rock hasn't been confirmed. It has its own protective magnetic field, and on the COSPAR planetary protection scale, this world ranks significantly lower and safer. But for a lander, one that would touch down on Europa itself, the problem looks completely different. Engineers have worked on lander concepts more than once, and sterilization in every single one of these concepts is always the hardest, almost unsolvable part. To bring the spacecraft's biological payload down to Europa's safe standard means literally baking the entire assembled craft in giant ovens at temperatures that inevitably damage delicate modern electronics, or engineers have to brutally restrict themselves to only those primitive components capable of surviving such hellish treatment. And that radically guts the scientific instrument payload, rendering the mission almost pointless. You'd think Jupiter's murderous radiation would help here, since it provides free sterilization of Europa's upper ice layer in a geologically short time. But this radiation protection covers absolutely nothing but the very surface. Any exploratory probe designed to melt through the ice and dive down into the hidden ocean automatically strips away this protection by definition. It would carry the microbes of Earth straight into pristine waters. That is exactly why today, there is not a single approved and funded project for a Europa lander mission. A lack of money is far from the only reason we still aren't drilling through that ice. Here is what we know for sure today. A solid ice shell, roughly 15 to 25 kilometers thick, safely covers a giant mass of liquid, warm, salty water 60 to 150 kilometers deep. Hidden in this darkness is more water than in all the oceans of our blue planet combined. This water rests on solid rock. It is warmed from the inside by the moon's constant tidal flexing and Jupiter's mighty gravitational field. And all of this is hidden beneath an icy surface that is geologically younger than our Rocky Mountains. A surface that some colossal internal force continues to renew over and over again. But here is what we do not know. Not a single scientist today can tell you for sure if anything at all lives in this endless water. Does the dark ocean touch an active volcanic seafloor in a way that provides a steady supply of life-giving chemical energy? Are the plumes of water vapor, faintly hinted at by blurry Hubble data and old Galileo logs, real, permanent geysers? Or are they random, or just an instrumental reading error? Even the exact thickness of the ice is still just a mathematical estimate. The powerful, ice-penetrating radar on the new Clipper spacecraft should start answering these questions around the year 2030. We have never once touched this moon. Not a single time in the 30 years since Margaret Kivelson's stubborn magnetometer at the end of a long boom figured out exactly what was hiding down there. Absolutely everything humanity knows about this greatest of extraterrestrial oceans was deduced from a vast distance, from a decoded magnetic signal, recorded on the fly by a dying spacecraft with a broken main antenna. And when this heroic spacecraft began to relentlessly run out of fuel, the people on Earth responsible for it simply sat down and calculated the dry arithmetic. They saw a level of risk that humanity simply had no right to accept. And they steered their greatest machine into the atmosphere of Jupiter to protect the fragile world that it had just discovered. Galileo burned up in Jupiter's atmosphere on September 21st, 2003. The global ocean it found has existed in the darkness of space for about 4 billion years, and it is still there today, right now, beneath 20 kilometers of solid ice, in absolute darkness, untouched by anything living from our planet. Someone in those offices had to make that incredibly heavy decision, sign the death warrant, and execute it in cold blood for the sake of future science. That woman was Claudia Alexander.